As far as the outside of our accumulator container goes, we got lightning bolt stickers visible from all angles. On top here, we've got our card number and our university. We've got high voltage always energized. Coming around here, we got the TSMPs labeled with HV plus and HV minus, and they're clearly red. On the back here, we've also got high voltage always energized, University of Cincinnati number 222. And we've got our MSD labeled right here. And we've got our voltage indicator, which is an analog voltmeter. So both high voltage always present, and whenever the needle is in the red, that's when the voltage is above 60 and it's high voltage. Our first steam built PCB is the HV Sense board. It handles air control, pre-charge, discharge, all that good stuff. On this side is low voltage, on this side is high voltage. These photo relays and actual relays are all rated for far greater than 357 volts, which is our maximum tractive system voltage. The board is conformal coated, as you can see with this UV light. It's conformal coated on both sides. And then on this other board, which is a copy of this board, I'll show you the spacing. So I got calipers zeroed, and we'll set them to just about 4 millimeters, which is what is the prescribed distance for boards conformal coating at our voltage level, which is 357 volts. You can see throughout that we are that our separation, represented by this white line, is greater than 1 millimeters. Separation is also on the back side. Here we have a second variant of our PCBs that are in the track system container. There are 5 copies of these, all identical. They are our BMS sense boards. They measure voltage, temperature, and debalancer. It is all high voltage except for this section here, which is where the ISO SPI is bridged, where it goes from high voltage to low voltage ISO SPI. And you can see here that this gap is about 15 millimeters, bridged by these voltage rated isolation transformers. On our accumulator modules, our voltage connections in the HV path are this one from the cells to this copper carrier bus bar. And this is bolted together with a nylon nut of this type, so. And the connection then from that to the rad lock is made with this also nylon nut, like so. We can go over the bolted connections in the accumulator and the high voltage path. The airs have bolted connections, and those are nylon nuts. Following the tractive system path into the MSD, this is a blind hole OEM component. We use nylon patch bolts like this for both this connection and this connection. Following this over, this is a crimped connection. Following this over, this is a nylon nut on both of these to hold this in place. Come back here, more airs. Also again, nylocs. Come back to here, where these are thread deforming nuts on the fuses. All right, we're going to show the separation between tractive system wiring and low voltage wiring. This gauge here is more than 30 millimeters long. And we'll use this as our test of whether wires are far enough apart. So, install tractive system through here. This is kind of like the first area where we may be coming into conflict. And you can see that there is a clear air gap between those low voltage wires down here and this high voltage wire up here, and a plastic insulating barrier between the fuse and this wire, as is required. This harness is very far away from any other tractor system components. The gauge clearly passes through. Here, this wire is protected from the tractor system by this insulating barrier. This is heat shrink that is UL rated, voltage rated, and moisture rated. All the heat shrink in here is as such and is listed in our ESF. So we got heat shrink through all these, so we don't really need to worry about any of these because these are all heat shrink with appropriately rated heat shrink. Same here for the gap between these tractor system cables and this IL line. Over here, we've got tractor system connections for our voltage indicator, and those run nearby low voltage harness. But if you look at our gauge, there's clearly separation between there. Following this along, the next part where we could be having a similar issue is right here, between here and here, or you can see very clearly that there's good separation between this bundle of wires and this bundle of wires. These IO lines are separated from here by this distance. This is an adequate distance, and then from here it's more than enough because we got heat shrink here. Following through here, you can see there's clearance between these TSMP lines and this low voltage harness. And there's also clearance between the lines for our, we'll use these. There's separation in this low voltage harness and this high voltage harness. Okay, you can see here the distance between this exposed bit of tractor system and this low voltage harness right here. And then on this is our USB cable, and it is also insulated with this properly rated heat shrink. And that concludes our walkthrough of the wiring. Bus bars are spot welded together of copper and nickel, and then those bus bars are spot welded to the cells, but there is no solder in the high current path in the modules or anywhere else in the battery. You can see the white Formex GK10 that we use as an insulating barrier between our cell stacks and walls. We also use black capped on tape to fill in all the gaps. We also have this white Formex insulation on our lid. To demonstrate that no track system wiring leaves the accumulator without going through the air first, you can see that this air has no wiring connected to it other than the main tractor system wiring. Same for this fuse. The only thing that is before the air is this sensing wire right here, this what we call HV plus on the unswitched side of the air, and that goes directly to our HV sense / air control board. All of our wires are fused either by this main pack fuse here for our tractor system wiring, or by fuses on boards like all these. Details can be found in our ESF. There are 3 exceptions to this. HV plus, where we pick up from the battery, tractor system plus, and tractor system minus. Now I'm going to demonstrate that those wires are less than 150 millimeters long. I've got this piece of cardboard that's 136 millimeters long. This is the HV plus wire right here, and you can see it's shorter than this cardboard. The TS plus, tractor system plus, is also right here. It's shorter than this cardboard. And the tractor system minus is right here, going to this connector, and it's also shorter than this cardboard. The airs and main pack fuse are separated from the rest of the tractor system by this 3D printed bit, which is ULV 94 rated and electrically insulating. We also throw some Formex on top here. All right, next I will demonstrate tools removal to maintenance plugs. All of our maintenance plugs are non-conductive. It's all plastic and rubber and heat shrink insulation, except for the metal bit down here where the contact's actually made with the red lock plugs. Our maintenance plugs are red lock connectors that are positive locking through this tab feature. This button here you press, and you hear nice little click when they go in properly. And we'll just demonstrate that the maintenance plugs can't be incorrectly installed. So for the outermost edges, they're zip tied to this board that carries all of our electronics. You'll see this one, it can't reach, it's not long enough to get over here onto here. It is, the perfect size to get on that guy, where it should go. Same over here, not long enough to reach over here. Tugging on it with all my might. For the rest of our maintenance plugs, they're supposed to be installed like this. They should not be installed, shorting these 2 terminals. And they can't, because this piece right here, this plastic 3D printed piece, holds these rad lock plugs apart so that they're too long to fit on here like this. So even if I press them together, I can't do anything. The fire retardant sheet on top of our cells is this piece right here. It is 3D printed, fire resistant, ULV 94 rated PC / ABS material. Our connector coming out of our main connector coming out of the pack is right here. It has an interlock that you can see here, and on the other side of it for these blue wires. The energy meter also obviously has an interlock right here, and our MSD has an interlock which is right here. Let's see, if you're curious, on the other side, there's 2 pins there, the interlock pins. So this is our charger assembly. Right here, we got the plug that actually charges the accumulator. You can see its leads are very orange, nice high voltage orange. We've got some TSMPs out here, and on the inside here, you can see that this line is fused. These are fused to 8 amps. Here we have our charger on the charging cart. Right after startup, we will turn the charger on. We will clear faults, turns on. You can see that our voltage indicator is working. It's indicating above 60 volts. And when we hit the E-stop, like so, it discharges to less than 60 volts in much less than 5 seconds. Go for it. We're currently charging. I'm gonna flash this, the battery management system with code that will throw a fault and stop charging. So once I do that, you should see the charger turn off. Now the charger's turned off. You can see down here we have an AMS fault.
And we're going to show the grounding of the charging carts. So we have our negative hooked up to the ground terminal on the plug, and then I'm just going to go around on the box. So if we go to the box itself, we read 0. If we go to the lid, we read 0. If we go to the lid in another place, we read 0. If we go to the cart itself, we read 0. If we go onto the charging box enclosure, we read 0. And I believe that is it.